Okay, thank you everyone for sticking around for the fourth talk in this session. John Mease is going to talk about building dashboards in Dash, but also scaling those with Dask with a K. So this will be really cool because it's awesome to see these Python projects kind of interacting with each other, being able to use Dask also for visualizations and stuff like we were seeing in the last talk. So this will be awesome. If you have any questions, go ahead and put them into the Q&A section inside of Zoom in the chat, and then we'll get to them. So you'll have about 25 minutes for the talk, John, and then we'll try to switch over to Q&A at the end, but go ahead and take it away.
All right, sounds good. Thank you very much. Just a little background, I serve as Chief Scientist at Plotly. I'm looking forward to having this opportunity to talk with the Dask community about ways that I see the promise of being able to use Dask and Dash together to build scalable analytic dashboards. So the talk has three sections. First, I'll introduce Dash and highlight some of the design choices that it makes to prioritize scalability. Then I'm going to highlight just a couple of features of Dask Distributed that are particularly useful when integrating with Dash. Finally, I'm going to walk through 4 specific architectures that can be used to build Dash apps that dispatch their computation to Dask. All right, let's get started talking about Dash. So Dash is a library. It was first released by Plotly in 2017. It was built for creating rich analytic web apps using Python instead of JavaScript. The front-end components are based on the React ecosystem, and there's a growing ecosystem of components developed by both Plotly developers and by other third parties who have built some really great stuff. As I'm going to talk about in more detail, Dash's architecture is really optimized from the ground up with horizontal scaling in mind. So to get a general sense of the kinds of applications you can build with Dash, I'd encourage you to check out the Dash gallery. There are examples here of a wide range of styles of Dash apps that you can make, and with applications to different domains and industries. So in addition to showing Plotly plots in Dash apps, the basic kind of user interface controls that you'd expect from any dashboard toolkit, there are a variety of specialized Dash components that are available. So I'm going to highlight quickly. So Dash Bootstrap components lets you build user interfaces with the Bootstrap layout and theming system. Dash DAC includes components like dials and knobs and gauges and digital displays that are used to build up like instrumentation style panels. There's a VTK.js support VTK.js has awesome support for a wide range of 3-dimensional surface and volumetric plots. So that's really nice to have as an option when you have that kind of data. DeckGL and Leaflet are options for really powerful mapping support, and DeckGL in particular for the great 3D mapping visualization support. Cytoscape has all kinds of great support for graph layout algorithms and interactive apps based on graph data. Circos is a neat library for displaying a variety of pretty sophisticated circular visualization, things like chord diagrams. That's as far as I'm going to elaborate on these first 2 goals. For this presentation, I really want to dig into this third goal and talk through how Dash's architecture is designed to efficiently scale as the user load increases. This is going to require diving into Dash's use of reactive callbacks, how it manages application state, and then I'll talk about how these design decisions are key to enabling this scalability property. So Dash uses a reactive callback model for implementing application logic. And to help explain what this means, I just want to take a quick step back and talk about the most ubiquitous example of a reactive callback model, and that would be spreadsheet formulas. So here I have a simple spreadsheet app where a user enters a number of hours and an hourly rate, and the quote unquote app uses spreadsheet formulas to compute the daily and weekly totals. So if you think about it in the vocabulary of programming languages, Spreadsheet formulas are basically callback functions. They are calculations that are executed in response to changes in the state of the application. But the interesting thing about spreadsheet callbacks, as I'm calling them, is that they declare their inputs and outputs. So the input cells are the cell reference variables in the expression, and the output is the formula's location in the spreadsheet. Given these, then the spreadsheet application determines when to evaluate the formulas in response to cell updates to keep everything synchronized. And this is very much how Dash's logic system works. So here's a version of the same app as might be written in Dash. In this case, the formulas become Python functions that input the values of the user input components, and then they return the result of the calculation as a return value from the function. So if you notice the per week function here on the bottom right, it inputs the result of the amount function. And so like a spreadsheet, Dash maintains basically a callback graph internally, and then it determines the order in which the callback needs to be evaluated to keep everything consistent. So another thing to just point out is while the Python callbacks are executed in the server portion of Dash, the current state of all of the components and this logic for determining which callbacks need to be executed, that all lives in the client. So the server doesn't actually know about the current state of any particular client. It really just answers requests from clients to evaluate these callbacks. To help put this all in context, I wanted to just compare the reactive callback model to a somewhat more common, we're calling it imperative callback model. So here's how this app might be structured if we're implementing a framework that uses imperative callbacks. So here, the callback functions are registered to execute when a particular input value changes. So instead of returning a value, these callback functions, they use this changed input value to imperatively update other fields in a layout object. So these updates can involve both the change value, but also involve looking up existing values in the layout. So for example, in the onRate change function here, the new rate is passed as an argument to the function, where the function looks up the current value of the hours in the layout and multiplies it by the new rate, and then assigns that back to the layout as the new value of the amount. Then the per week value is calculated and assigned to the layout as well. And in this case, the responsibility in this architecture, the responsibility of the framework is to detect these changes to the layout and then to synchronize them from the server to the client. This approach can be really convenient for a lot of use cases, but an important thing to understand is that a consequence of this model is that the server needs to maintain a separate copy of the application state, something like this layout object in these callbacks. It needs to maintain that client state for every active user connection. To summarize, here's a breakdown of what is stored on the server versus the client in the Dash app. So starting with the client or the browser in this left-hand column, as I mentioned, the client stores the app layout and the callback graph for the app. And in fact, the client stores all of the application state that is specific to one particular user session. The server stores the Python callback definitions and any state that's common across all clients. So these are things like any pandas data frames that the app is serving, or database connections, or Dask cluster connections. And in particular, the server does not store any of this per user session state. So together, these design choices enable several benefits. First, because no user session state is stored on the server's memory usage actually holds constant as the number of simultaneous user connections increases. For systems that do store per user session state on the server, there's a cost associated with each active user session. And so it's standard practice to employ a timeout to terminate user sessions when a user is inactive for a certain period of time in order to free up resources. So Dash doesn't need to do this, and so you can keep a Dash app open in a browser tab for days without losing your current active session. And finally, because the state model, consecutive requests from a single client don't need to be handled by the same server process or even the same web server. This makes it possible to employ like arbitrary load balancing policies. Whereas systems that do store like user session state on the server, they'll typically need to ensure that all requests from one user get handled by the same server. And that limits the effectiveness of load balancing that you can use. Here's a diagram of what it looks like to serve a Dash app from a single server. And here I have server in quotes because this could be a physical server, this could be a VM or a pod or a dyno, something like that. Here I'm using showing the G-Unicorn web server is used to launch multiple independent processes that each serve an instance of the Dash app. The server binds a socket to an external port like 443, and then each web server process listens for requests on the socket. Clients connect to the server using this external port, and in this configuration, basically the operating system serves as a load balancer because as clients make requests to the server, the operating system will dispatch those requests to whatever process is ready and waiting on that socket. This single server configuration can go a long way, especially if you're using a powerful server and you can launch a bunch of web server processes on it. But when that's not enough, a load balancer can be used to serve an app across multiple servers. But here, each server can be running multiple instances of the app in separate processes. A load balancer could be Nginx, it could be Plotly's Dash Enterprise on Kubernetes, or a load balancer from any of the major cloud providers. And in any case, to optimize response time for the clients, the load balancer has full discretion to independently dispatch each client request to any available server. So it could use a round robin policy, cycling through all the servers, or even better, it could use like a least connections policy that would forward requests to whatever server is currently processing the least number of requests, things like that. And then there are a bunch of other load balancing policies that are also different cloud service providers do that are based on memory usage and computation, and low-level statistics that are available through Kubernetes and that kind of thing. Okay. Now it takes a couple minutes to highlight a few features of Dask Distributed that'll largely be reviewed, but I just want to highlight them to tie into how we're going to combine Dask and Dash in the future architectures. So as you're probably familiar with, Dask Distributed can operate in a local cluster mode where the workers, scheduler, and clients will all run on a single server. And just to review terminology, here clients are the Python processes that connect to the scheduler to request computation from the cluster. Examples would be like a Jupyter kernel or a Dash app. These could all be Dask clients. The workers are the Python processes that actually execute the requested computations. And the scheduler's job then is to coordinate this work among the workers. Using Dask CUDA, individual workers can be associated with an NVIDIA GPU on the server. In this diagram, we're using a server that has 3 GPUs. Each one is associated with a single Dask worker. And this arrangement makes it possible for the clients to request calculations backed by rapids libraries like cuDF or CuPy or TensorFlow, or client could be using a library like Blazing SQL that manages its own connection to the Dask scheduler. Finally, in a distributed cluster configuration, the workers, scheduler, and clients all reside on different servers. In this case, you would typically be using one of the Dask deployment libraries to manage the scheduler and workers, things like Dask SSH or Dask Yarn, JobQ, Dask Gateway, Dask Kubernetes, or you could be using one of the managed Dask services like Coiled or Saturn Cloud. Finally, I wanted to highlight 2 particularly useful Dask distributed operations. And these are persist and publish. So persisting a data set triggers the full execution of the task graph. So that could include loading the data, pre-processing, filtering, any EDL you need to do before you want to visualize it. But instead of returning the results to the client the way .compute would, the results are stored in memory across the workers on the cluster, and then a task graph referring to these pre-computed results is what is returned to the client. Moving on to publish. So any client connected to a distributed cluster can publish a data set, which is simply the act of associating a name with a particular task graph. So once the data set's been published, it's immediately available by this name to all of the clients connected to the cluster. Okay, now finally, I want to talk through some approaches that can be used to combine the strengths of Dask Distributed and Dash to create scalable analytic dashboards. So here's the first architecture that I want to walk through. And I'm going to talk through this from right to left. So starting on the right, you'd have a web browser client that would interact with the dashboard and send a request to, in this example, send a request to the load balancer. Um, The load balancer then would dispatch that request using whatever load balancing policy is currently in effect. It would dispatch that request to one of a pool of servers that it is managing. In this configuration, each server is running its own independent local Dask cluster with its own scheduler and its own collection of workers. And each Dash web server process, these are things that are launched by something like a unicorn, has its own Dask client that connects to that scheduler so that it can send calculation requests to the local scheduler. And these requests are executed by all of the workers on the server. At the application startup, you would have a script where each server would load and then persist and publish the data set that the app needs to the cluster so that it's in memory and fast and ready to go when the app makes interactive requests of it. So this architecture is a good choice for an app that's working with what I'm calling a medium-sized data set. So this is something that's larger than what you'd want to handle with pandas or NumPy, but still that could fit comfortably in the memory of a single large server. So out of that, you get Dask CPU parallelization. And for a fixed size data set, this approach can scale to handle more and more users by simply replicating these server units that contain both the web server processes and the local Dask cluster. There's nice simplicity benefits of this setup because you don't need to separately manage a shared Dask cluster. So you can independently add and remove and restart these servers without having to coordinate between them and a cluster. There's also simplicity in the fact that the Dash app and the Dask workers can literally use the same environment installation, so you don't have to worry about having out of sync versions of your dependencies and packages. That all just works out. The second architecture, it's very similar to the first one, but now the local Dask cluster on each server is replaced by a local CUDA cluster. This makes it possible for the Dash app to use parallelized GPU calculations across the GPUs on the single server. Again, the app's data set is persisted and published to the GPUs on startup. And the mapping of a single Dask worker to a single GPU is important because this ensures that the GPU will only be, a single GPU will only be processing a single request at a time. And this helps maintain like a bounded memory usage for the GPU so that you don't end up having to run out of memory or spilling over to RAM or disk when a lot of requests are coming in at the same time. So this architecture, again, is a good choice for a medium-sized data set that can fit comfortably in the combined memory of the GPUs on a single server. You obviously get the benefit of GPU parallelization. And as with the previous architecture, the app can scale horizontally to support more users by replicating these server units that each run both the Dash web server processes and the local CUDA cluster. In this third architecture, the Dask scheduler and workers are now extracted into a standard Dask distributed cluster. So this would be managed by one of the Dask cluster management libraries or a service like Coiled or Saturn Cloud. So now there's a single scheduler that all the Dash web server processes connect to. And that scheduler has access to all of the workers across the cluster. The data set, again, you'd want to persist and publish to the cluster before launching the apps. But something to keep in mind is that this process of preloading the data set, it can't be performed by the individual servers, web servers anymore, because there's one central copy. So you'll need some external process to manage the presence of that data set on the cluster. This architecture enables the Dash app to work with a data set that's larger than what could be handled on a single server. The calculations can be distributed across all of the Dask workers in the cluster. And also, of course, you could have the cluster configured with GPUs for Rapids or TensorFlow support if you needed to. This architecture can also scale to support more and more users, but now since the compute load will increase with the number of users, the Dask cluster will also need to scale horizontally along with the Dash web server. So that introduces a little bit more complexity, but is, of course, is manageable. But compared to the previous architectures, there's also more complexity needed to manage this configuration because the cluster always needs to be running before the Dash app so that the Dash app has something to talk to request computation from. And also the Dash app and the Dask workers are no longer sharing the exact same environment installation. And so you need to worry about all these issues of having compatible, ideally identical environments installed in both places, both for the Dash app's web servers and for the Dask workers. And so finally, what we really want is for the Dash web server pool and the Dask cluster to both scale dynamically in response to demand. Where here demand includes both the number of simultaneous users, the simultaneous user sessions, and the size of the data set that's being processed. This would enable elastic scalability to adjust both for dataset size and user traffic. Several of the Dask distributed management approaches and the managed services already support forms of auto scaling on the Dask side. On the Dash side, it'd be possible today to hand roll a auto scaling approach where you'd use one of the cloud service providers auto scaling approaches, and you replicate the servers dynamically based on load configuration parameters that you would set up. But one of the things that Plotly is focused on, just wanted to quickly mention, is that the next version of Dash Enterprise is going to have this as a focus area to make this easy to independently scale the web server pool in response to load. And with that, I'm happy to open the floor for discussion and questions. I think there's a lot of interesting things we could talk about, but I want to end there.
Okay, awesome. Well, thank you, John. That was really cool to see, and I love the architecture diagrams. Very clear and very easy to understand. So thank you for that. If anybody has questions, go ahead and post them in the Zoom Q&A or in the chat. We do have one here, which I think is just more about Dash in general. Does Dash have a good solution to having the dashboard update in response to server state changes?
Yeah, this is a good question. So the approach you use is to have the clients check, basically. There's like it's called an interval component that you'd use to set an interval for the client to check, basically, if there are updates, and then the server can respond with nothing if there aren't updates, or can respond with a new data set. There is like some people have done some in the community have done some experiments with hooking up like a WebSocket kind of solution to push to push results from the server to the clients. A challenge with WebSockets, and they're very powerful, but they limit the load balancing advantages that I talked about there. So when you're using WebSockets, you do keep this persistent connection open between a server and a client. And so you have this sort of requirement for a sticky association that that you lose some of those benefits. So typically people will go with the polling approach unless there's a particular specialized need.
Gotcha. Okay. Go ahead, and like I said, everybody can add some questions. I do have a couple actually. Back to maybe like the first or second of the of the architecture diagrams that you shared. It was more of like a clarification from my perspective, for me, is that when you're talking about like the horizontal scalability, that's about like when you have more and more groups of users, and then you're basically creating or attaching like a new machine that now has its own local Dask cluster. And that's kind of the horizontal scaling part, where you're going to keep adding more and more of those machines as needed. Is that kind of how that works?
Yeah, yeah. So like you get these, when you're configured this way, you have these pods of, or not pod in the Kubernetes sense necessarily, but you have these units that include both the computation and the web server features. And once you have this scaled to match your data set well, you can replicate as many of these as you need behind the load balancer, whether dynamically or just manually to decide how far you want your app to be able to scale to start with.
Okay, that makes sense. And is it possible, or it wouldn't even be worth it to have like multiple local clusters on the same like large machine? Because then you don't have the environment problems like you were talking about, but you could kind of still maybe scale those up. And I guess you're paying for the machine even if you're not using it, but would that even be like a feasible architecture?
You said again to use
To use
multiple local
get
clusters
like
on one
one
server?
large machine, yeah, and do like multiple like Dash clients, and then multiple like local clusters that only have like, you know, a fraction of the hardware resources on that machine.
So in this case, I mean, definitely it's advantageous to use like a bunch of web server processes to independently serve the web app part. I don't know if there would be an advantage to using multiple like schedulers on a single server. I mean, so here the idea is you have a single scheduler on one of these servers and as many workers as were reasonable for the hardware that you have. And in this configuration, like you could load your environment from the same like local disk for all the workers and the Dash web servers. Is that in the ballpark for your question?
Yeah, that's kind of what I was thinking, just maybe like another option of doing things. um, okay, well, I'll give everybody just like 5 more seconds if you want to drop in another question. Going once. Okay, well, awesome. Thank you so much, John, for the talk. It was really great.
Thank you. Great to have a chance to talk with you all.
All right,
See you around.
that concludes today's session, or at least this session. There's definitely plenty of other sessions on the schedule, so go ahead and check out the Summit website, and there's other workshops and talks going on the rest of the day. So thanks again, everybody. Bye-bye.